Chapter 10 of your textbook is on analyzing quantitative data. Chapter 9, which I did not require you to read, was basically explaining how we use statistical software programs to input the data from our questionnaires into this program, and then we're able to run statistical analyses using the program. For those of you that go on to take the upper level quantitative methodology class, you are going to learn how to do this with a statistical software program. So the goal of this chapter isn't really to teach you how to do it, and it's not even necessarily, making sure that you understand, mathematically, the equations of how to calculate certain measures, but it is kind of focused on making sure you understand the logic behind statistical analyses, as well as how to interpret it when you see, when you read about these measures and analyses in your sources that utilize quantitative methodology. So I'm going to begin this chapter by, as always, just kind of reminding you of some key ideas and concepts. And then I'm going to introduce a couple of new concepts, and then I'm going to get into the actual textbook material. So as always, a reminder that in sociology, we conduct both deductive research as well as inductive research. Deductive research is that typical research model where you begin with ideas and you collect data in order to test those ideas. And in deductive research, you formulate a hypothesis. And although this can be both qualitative or quantitative, it usually is quantitative methodology. With inductive research, you gather data first, and then you kind of develop your ideas. And you aren't necessarily comparing it to what's already known about your topic. So you don't formulate hypotheses. Instead, you have open-ended questions. And this type of research is almost always done with qualitative methodology. And so just a reminder that quantitative methodology is methodology that collects data that can be quantified, that can be turned into numbers. It is particularly useful when you want to explain relationships between variables. It's particularly useful when you're wanting to generalize to larger populations, because you are able to have larger sample sizes with this type of research. Comparatively, qualitative research is data that cannot be quantified. It is going to be, it has some limitations in terms of sample size, but the trade-off is although your sample size is smaller and it usually is not representative and you can't necessarily generalize it, it does provide in-depth knowledge of social life, institutions, processes. And so in sociology, people do both types of research. And regardless of whether or not you are doing qualitative or quantitative research, almost all research is sample-based research, not population-based research. Population-based research is when you are gathering data from the entire group of people who are the focus of the study. This type of research is very time-consuming, it's costly, it's hard to administer. So oftentimes, instead of population-based research, we do sampling, which is where we select a subset of the population. We call that the sample, and we collect data from that subset. And there are many different ways in which you can sample. If it is really important to you that you have a sample that is representative and that can be, and that you can feel confident generalizing your results to the larger population, you probably want to go with probability sampling. But probability sampling is based upon you having a sampling frame, a list of the entire population that you have access to for your study, because you randomly sample that, you randomly sample using that list. So if you don't have a sampling frame, you aren't going to be able to do probability sampling. You're going to have to do non-probability sampling. Although sometimes, probability sampling isn't even necessarily useful or desirable, particularly if you're not trying to generalize your results to the larger population. In which case, you might just choose to do non-probability sampling. So for this chapter, our focus is on, quantitative methodology, whether we get our sample through non-probability or probability sampling techniques. But, we are doing this quantitative methodology, whether that's some type of experimental design, non-experimental design, quasi-experimental design, but we are collecting that data. We're collecting that data that can be quantified. And generally, how we collect that data is in the form of closed-ended questions, because that is what allows us to easily quantify our answers. Now, those questions were either created by you or someone else in the process of operationalization, which is the process through which we turn our constructs into variables. But once you have those variables and you collect that data using those variables, the variables themselves can be qualitative or quantitative. And this is something that I know that trips some of you up, right? Your questionnaire, your closed-ended questionnaire isn't necessarily just all quantitative variables like that, all variables that are related to values resulting from counting or measuring. Your closed-ended questions can also be qualitative variables, which also are called categorical variables. And these are variables that are trying to measure attributes that aren't related to measuring or counting. Now, your book doesn't necessarily introduce the idea of nominal, ordinal, interval, or ratio. Your book does introduce the concepts of discrete and continuous, which is a very specific form of quantitative variable. So I'm going to talk about all of these. So nominal, these are categorical qualitative variables where they don't actually have some type of natural order, right? So this would be if I was asking a question about hair color, ethnicity, what's your favorite pet, right? That is a categorical variable, right? Because it has nothing to do with numbers, nothing to do with measurement, nothing to do with counting, but it's also what we call a nominal variable, because those values, those answer values they don't have any type of inherent order. We can't rank them in any kind of logical or sensical fashion. Now, ordinal variables, it's right there in the name. They too are categorical variables, but they are they have a kind of inherent order. So this would be like student letter grades, A, B, C, D, and F, right? They have an order. This could be things like school classification for first year, sophomore, junior, senior. This could be like our scales, right? Strongly agree, neutral, disagree, strongly disagree. So once again, we're collecting, these are qualitative variables, but they're ordinal in the sense that the answers themselves are ordered, and you have to, when you are writing them, when you are giving the questionnaire, you have to present those possible values in the correct order. Then we have our we have our quantitative variables, and these are values that result from counting or measuring. So, you know, as your book discusses, these types of variables can be discrete or they can be continuous. So discrete are whole numbers that can't be broken down, right? So if we're asking a question, how many baby teeth did your child lose at the, you know, during their 5th year? Right? You don't lose 1.5 teeth. You don't lose 2 7/5 teeth, right? Those are discrete numbers. You say 0, 1, 2, 3, 4. Another kind of like discrete, you know, how many pairs of shoes does this person own? Once again, you don't own 1 1/3 of a pair of shoes, right? You own 1 pair of shoes, 2 pairs of shoes, 3 pairs of shoes. So those are discrete quantitative variables. You then have what is called continuous quantitative variables, and these are numbers that can be broken down into, you know, fractions and proportions. And really, that's the most important thing you need to know. But just additionally, you can just be aware of the fact that there are interval continuous variables and there are ratio continuous variables. And although that distinction between interval and ratio is not very significant for this class, just know that, you know, part of it has to do with, you know, how we define it is an interval variable does not have a true zero, while a ratio variable does. So temperature in Fahrenheit, you know, there isn't a true zero. SAT scores, there isn't a true zero. IQ, there isn't a true zero. Year, not a true zero. While ratio, there is a true zero. Age, height, weight. Like I said, for this class, that's not really necessarily significant. It is much more significant, though, that you understand that there is this distinction between qualitative variables and quantitative variables. Nominal and ordinal are qualitative variables. Interval ratio are quantitative variables. Quantitative variables can also be thought of as being discrete or continuous. So that is just a little bit about variables. And of course, it's these variables that, and you know, that our variable data that we are going to be analyzing. And that is what this chapter is about. So now I'm getting into the material from this chapter. So, you know, this chapter begins by giving you the definition of statistics, you know, that this is a form of mathematics that we use in order to conduct data analysis. And that furthermore, we can think about this statistical analysis as being broken down into univariate analysis, where you're focused on analyzing only one variable. Bivariate analysis, which we're going to focus a lot on univariate analysis. We'll talk a little bit about bivariate analysis, where you're looking at the relationship that exists between 2 variables. And what we are not going to discuss at all, because it's really beyond the scope of this class, is multivariate analysis, where you are looking at the relationship between multiple variables. And it's just worth noting that, you know, for the types of research that you mainly, you know, read, you know, in your academic journals, a lot of that is multivariate analysis. But analysis almost always begins with univariate analysis. And that's because univariate analysis allows us to do 2 things. It allows us to engage in descriptive analysis, where we familiarize ourselves with our population sample. This type of descriptive univariate analysis, it tells us important things like minimum and maximum value, range, quartiles, mean, mode, median, outliers, number of missing answers, understanding the variable's distribution. We can get that information for each variable in our data set. So if you had a question with, you know, 50 questions, that means you have 50 variables. And for each variable, you can engage in this univariate descriptive analysis that will tell you about the range of answers to that one question, to that one variable. The other way that we use univariate analysis, and we're going to not focus as much on this type of analysis in this chapter, is that, you know, it is something that we do when we are engaging in inferential analysis, where we are trying to make inferences about our larger population, because keep in mind, this is based on our sample. So we want to be able to generalize from our sample to our larger population. And so we want to kind of understand what are the relationships that, you know, how we want to be able to describe our sample on the basis of these individual variables. We want to understand the relationships that exist between variables in our sample. And we want to understand to what extent is this representative and generalizable to the larger population. And so your book kind of discusses like one specific way in which univariate analysis is used in this capacity is to try to calculate random error. You know, and this is the error that occurs during data collection. So it's previously been discussed in this class in terms of sampling error. So, you know, we can kind of see to some extent what type of random error exist in our sample by comparing, you know, what we've collected about our sample to what is known about the larger population. You know, and there are methods for how you go about doing this. Once again, that's kind of beyond the scope of this class. So just kind of understanding that this is one way in which we use univariate analysis is to establish, you know, the amount of random error that exists around specific variables within our sample. And then just note that, you know, this is less useful and less feasible if the type of error is systematic as opposed to random. But the bulk of this, of our discussion on univariate analysis is related to, you know, descriptive, I'm going the wrong way, descriptive analysis, where we are kind of learning about individual variables, you know, learning about their distribution and their other kind of qualities. So beginning with kind of our first, you know, what we might know about a variable is that we can analyze that variable to discover its frequency distribution. And a frequency distribution just kind of tells us, you know, it describes the key characteristics of participants in the sample. And if we're talking about absolute frequency, it's the number of times that a value was given by the members of your sample for that particular variable. So if you look at the frequency distribution chart here, that looks like it's related to educational classification. We know that in our sample of 435 people, that we have, for absolute frequency, we have 147 freshmen, we have 96 sophomores, 98 juniors, and 65 seniors. And we have 29 missing cases for this particular variable. So your book talks about cumulative percent. And that is where you basically are turning your frequencies into percentages. And then once they're turned into percentages, you can formulate cumulative percent, where you aggregate the percent category by category. So you take the percentage of freshmen and then you add it to the percentage of sophomores, and that gives you a cumulative percent of freshmen and sophomores. And then you take the cumulative percent of freshmen and sophomores and you add to it the percentage of juniors, and then that gives you a cumulative percent for everyone that is, you know, not a senior, and so forth. And by the time you get to your final value, your cumulative percent adds to 100. Now, if you have a variable that, you know, has missing cases, missing data, then before you do cumulative percent, it's probably helpful to do what's called valid percent, which you recalculate your percent, but instead of using the total number of cases, you use the total number of cases minus the missing cases for this variable. So for this, in order to calculate, in order to calculate valid percent, instead of dividing 147 by 435, you take 435 and you multiply, or I'm sorry, you subtract 29 from that number. So you have 406. And so you divide 147 by 406, and then that gives you the valid percent. And they base the cumulative percent off of the valid percent as opposed to just the percent. Cumulative percent really only makes sense if you have ordinal variables. Order is important for cumulative percent because it's the sense of, there is some type of logical reason why you would want to know, these kind of cumulative aggregates as you move up or down, the list of values. So univariate analysis, part of how we're going to talk about, beyond frequencies, we're going to talk about central measures of tendency and then central measures of variability here in a second. But in general, as opposed to just telling people those things, it is a lot more eye-catching and easier for people to engage with if you present it to them in graphical depiction, as opposed to, just writing it or even just putting it in a table or a chart like what we were just looking at. And so there are common types of graphs that people use in order to represent this univariate, these univariate statistics. And your book talks about it says bar groups, bar graphs, histograms, line graphs, and pie charts. So bar graphs use vertical bars that represent the values associated with a specific variable. The length of the bars represent the frequency. And so you see there that, these bars don't touch, and you can use, for this, it can be either your qualitative categorical variables, either nominal or ordinal, or you can have your quantitative variables, particularly if those variables are, discrete, meaning, separate numbers as opposed to continuous. So that's what a bar chart is for. If you have those continuous variables, your interval or ratio variables, then you might, it's better to use a histogram. So these are used when you are wanting to depict quantitative variables that aren't discrete, and where the categories are related to one another, like where one category kind of runs into right up to the next category. And you represent this by having bars that touch. And so you can kind of see the distinction between, a histogram versus a bar chart. Now, line graphs are when line connects points in a distribution. And they are usually much more useful when comparing multiple related variables as opposed to just one variable. So this is, much more useful when you're talking about like a bivariate analysis or a multivariate analysis. Although, you can use them for univariate analysis, but just in terms of utility, it's more useful if you are talking about more than one variable. And then finally, you have pie charts. And these are a very straightforward representation of categorical variables. So particularly nominal or ordinal variables. And it usually works if there's a relatively small number of categories, because you are showing the proportion of responses for that value comparative to, the whole. So these are very eye-catching and straightforward, and a lot of people find it very easy to interpret pie charts, but they certainly cannot be used for all types of variables. So now let's talk a little bit about the types, beyond frequency, what else could we study and be interested in terms of univariate descriptive analyses. And so we're going to talk about measures of central tendency first. And so measures of central tendency, this is a really popular form of univariate statistical analysis, because this basically summarizes your entire variable into a single value that is meant to numerically represent the entire variable. And the most popular measures of central tendency are mean, mode, and median. And of the three, the most popular one, the one that you're most probably familiar with, is what we call the average, but what is actually referred to as the mean. And this is where, the mean is the mathematical average of a set of numbers. You add all the numbers and then you divide them by the total entries in the data set, and then this gives you the mean. And you can kind of see an example of what that looks like there in the little picture. Now, the median represents the center point in a set of numbers. And how you get the median is you organize your numbers in either ascending or descending order. And so these are like all of the responses that people in your data set gave. So that means that some numbers can in fact repeat. So, if I was asking about like ages of people in my class, and like 15 of you are 19 years old, I wouldn't just write the number 19 one time. I would write the number 19, 15 times. And then once you have written all the numbers or organized all the numbers in this order, if you have an odd number of cases, then it literally is just the middle number, the number right there in the middle. If you have an even number, it is the middle two numbers that you then divide by 2. It's the average of those two numbers. Now, one reason why the median is useful comparative to the mean is because it really tells us, it illustrates the distribution of responses within a variable, and it's a lot less sensitive to outliers. So what does that mean? Like, let's say that I was asking my students about the number of pets that they had at home, and most of you had between 0 and 2, but like, let's say one person lives on a working farm, and they decide that they interpret my question to include their farm animals, and they give a response that's like 200. Well, if I add up all of the people that that said 0 and 2, but then I also add in this person that says 200, then that is definitely going to influence what the average is going to be. It's going to look very high. And that isn't necessarily the best representation of the data set, right? Because I had this one outlier. If I instead use the median instead of the mean, then the fact that I have this one person as an outlier, that isn't going to really influence the median, because the midpoint is going to still largely be the same. The last type of central tendency measure we're going to discuss is mode. And this is the response that's most frequently used. So this is like, going back to my pet example, if 18 students say that they have one pet, and that is the most common answer, then 1 is my mode. And for this reason, out of all the measures of central tendency, mode is the one that's least sensitive to outliers. Like, outliers don't matter at all when you are looking for the mode. Now, if there's just one mode, then we call that unimodal. If there are 2 answers that occur in equal numbers, then we call that bimodal. If there are multiple answers that seem like they are most common, then it's multimodal. And honestly, when it's a multimodal distribution, it almost at that point is really just almost doesn't even have a mode, because like what it's basically saying is that there were multiple answers that were common. So there really is almost no answer that then, or there isn't one value that then like reflects the measure of central tendency. There is no central tendency for the most part if a variable is multimodal. Now, outside the scope of this class, but just so you know, different measures of central tendency are more or less appropriate given the type of variable you're working with. So, obviously, nominal variables, which are straight categorical with no real order, you can't do a mean, you can't get the mean or median for that type of variable. While you can, of course, get all three if you're talking about like an interval or a ratio type of variable. And similarly, with ordinal variables, you can get the mode, you can't get the mean, you can get the median, and that's just because you can organize, because ordinal variables, you do have like a unique order system. You can in fact get the median, but you can't get the mean. So just kind of know the type of univariate descriptive analysis you can engage in for your variable is somewhat determined by the type of variable that it is. So opposite of measures of central tendency is measures of variability. So what is variability? Variability expresses the degree to which data in a data set spreads out, deviates from the center. At the center are our measures of central tendency, mean, median, and mode. So from that point, data can then range in how distant data points are from that measure of central tendency. So if the points, our data points largely are all clustered around the center, then we might say we have very little variability in our data set. Our data set is homogeneous in regards to that variable. But if our data points are far reaching, if they're pretty distant from that measure of central tendency, then we would say that we have a lot of variability in regards to that variable. In that case, our data set is heterogeneous in regards to that characteristic. And so just like we have specific measures of central tendency, we also have specific measures of variability, also called measures of dispersion. And those specific measures, the ones that we're going to be focusing on in this class, are range, interquartile range, outliers, variance, and standard deviation. So range is the difference between your largest and smallest numbers in the set, your maximum value and your minimum value. Because you are doing math here, obviously this is only appropriate with quantitative variables, whether discrete or continuous. So you subtract your lowest value from your highest value, and you get a range. A larger range reflects more variability. A smaller range reflects less variability. Now, interquartile range is what we use in order to define if we have outliers in our variable, and what we should consider to be an outlier. So to find interquartile range, first we take all of our data points for that variable, and then we organize them by ascending or descending order, and then we divide them into 25% chunks, and so quarters, if you will, because that's what quartiles are. So we divide them into quartiles. The first 25% is Q1, the second 25% that goes right up into the median is Q2, and then the third 25% is Q3. And then Q4 we don't really discuss, but that takes you all the way up to your maximum data point. So to find the interquartile range, what we're doing is we are subtracting the data point at Q3 with the data point at Q1. So what data point is at the 75th percentile and what data point is at the 25th percentile, and that gives us our IQR. We then take our IQR and we develop kind of our parameters for what should and should not be considered an outlier. So you see that the outlier formula is this. It is for on your higher end, what are your outliers? It's Q3 plus 1.5 times the IQR, Or our low outliers, it is Q1 minus 1.5 times IQR. So if a value is lower than that Q1 minus 1.5 times IQR, we consider that a outlier. And if our data point is higher than our Q3 plus 1.5 times IQR, we consider that an outlier. And so this is important because for certain types of analyses and certain types of distributions, it sometimes just makes sense to eliminate or, to not include outliers in your analysis. And this is how you determine which data points are outliers. So then we get to our most sophisticated measure of variability, and that's variance and standard deviation. I remember having to learn how to do this by hand, and I do give you kind of a look at what that calculation looks like. And perhaps you have taken statistical math classes where you've had to calculate the variance and standard deviation by hand. You aren't going to have to do this in this class, but understanding, like, first of all, what these two are, how they relate together, and then how we then interpret them and use them is key. So they're very closely related, because variance is the average sum of the squared distance of every single point in the data set from the mean. And then standard deviation is just the square root of the number. So standard deviation is the square root of the variance. And so what you see in that example is you have 8 data points, and you add them up and you divide by 8, and it gives you the mean of 5. And so then in order to get the variance, what you see is each data point, you subtract the mean, and then you square it. And then that is what gives you, this number that you then add. You add all of those numbers up, and then you divide it by the mean, and then that gives you the variance. You then take the square root of the variance, and then that gives you the standard deviation. And the standard deviation, how we interpret it is, this is the average range around the mean. So, for our example, we don't really know what these data points mean. I see a bunch of 2s, 4s, 5s, 7s, and 9s. Let's just say, for my made up example, that this variable was the number of close friends that you have in your life, right? So the question said, how many close friends do you have in your life? And people said 2, 4, 5, 7, and 9. These were the answers from the 8 people who were in my sample. And so this results in a standard deviation of 2. And so this means that the measure of central tendency is 5. So I would say the average number of close friends that a person has in their life is 5. However, there is a standard deviation of 2, which means that it also, on average, the range in which people fall for this answer is 3 to 7, right? 2 less than 5, and then 2 more than 5. So I could say that most of the people in my sample fell between 3 and 7. And if you look at the responses, you'll see that that's true. I only have one person that was less than 3, and I only had one person that was more than 7. So that's how you think about and how you talk about the standard deviation. And that concept of the standard deviation relates to the last 2 measures of variability that we're going to discuss, which is normal distribution and z-score. And these aren't really measures of variability, but these are important concepts that kind of relate to variability. So the normal distribution is the perfect theoretical distribution where the mean, mode, and median are perfectly equal to one another. And what this looks like graphically is that symmetrical bell curve. And you probably have seen this, you probably have seen this image in textbooks or, what have you. It's considered to be theoretical because it usually doesn't really exist in terms of real data and real research. It's extremely rare to get this perfect normal distribution. And we'll talk about why this is in upcoming slides when we talk about skewness. But even though it doesn't really occur, it is still useful theoretically. And that's because we use this concept of the normal distribution in order to establish what are called z-scores or standard scores. And this is based upon this normal distribution. And what it establishes is the number of standard deviations in a distribution. So z-scores are used to tell us how many standard deviations are found within a distribution and what proportion of the data set falls within this range. And so under a normal distribution, right, within one standard deviation, 68% of your data in a normal distribution is supposed to fall within one standard deviation. And when you're talking about two standard deviations, then 95% of your data is supposed to fall, up under, within that portion. And then finally, if you're talking about within three standard deviations, 99.7% of your data is supposed to fall within that proportion. Like I said, do not be overly concerned. It is largely beyond the scope of this class to be overly concerned about, the math behind this, or, specifically how do you calculate z-scores. It's really just kind of important to know that this is why we have a normal distribution. This is why we've created this theoretical, graphical depiction of this distribution. Is it allows us to calculate or to establish these standard scores, these z-scores, and then there are analyses that require you to use your z-scores. You aren't going to learn how to do these analyses in this class, but it's more like when you do get to the classes that require you to do things with the z-scores, just understanding where they come from. So, as I noted, most distributions do not behave like the normal distribution. They lack that perfect symmetry where the mean, median, and mode are in the center. Instead, most distributions are asymmetric in shape. Like if we were to graphically depict them using a histogram, they would not look like this normal distribution. They instead would exhibit some level of skewness. And skewness can be either left or right-sided depending on the data. A left skew has a long tail on the left, which means that, you have some outliers at the lower range of your scores. And we call this negatively skewed. And a right skew, it looks like the graph, the graph on top, where you have some outliers at the higher end of your value range. And we call this positively skewed. So you kind of know to what extent your distribution is positively or negatively skewed if you compare your median, mean, and mode. If you compare those values, if you have a mode that is lower and a mode and median that are lower than your mean, you probably have a right skewed, positively skewed distribution because your mean is high because you have some high outliers that are pushing your mean higher than your mode and median. If your mean is lower than your median and your mode, then you have a left skewed distribution, a negatively skewed distribution, and that's because you probably have some low value outliers that are making your mean, when you calculate your mean, making it to be lower than the median and the mode. And so that's it for univariate analysis. We then move on to our bivariate analysis. And I'm going to spend a little bit less time on this analysis because I feel like a lot of this makes more sense when you're actually doing it, using the statistical program. So I just kind of want you to think about this in terms of, I want you to logically understand the concepts of correlation and regression. I don't expect for it to be perfectly clear because I am a big believer in you will gain a lot of clarity around these concepts when you are actually doing doing this type of analysis with actual data. But I do want to understand, I do want you to begin thinking about and to begin understanding the logic behind these types of analyses. So bivariate analysis is basically, the type of analysis where you're investigating the relationship between two variables. You're particularly interested in how the changes in one variable impacts the changes in the other variable. And while there are many different ways two variables can relate, this text focuses on two. And then I did not put those two down. So hopefully you're listening to this video so you can correct this mistake on the slides. But this text focuses on two ways. It focuses on correlation and it focuses on regression. Before we talk about correlation and regression, let me discuss scatter plots, because they're going to come up as we are looking for ways to graphically depict both correlation and regression. And this is just the visual depiction of a bivariate relationship. Scatter plots are dots on a graph that represent the relationship between two quantitative variables, a variable that you are deeming to be dependent, and a variable that you are deeming to be independent. And the IV is on the x-axis and the dv is on the y-axis. And each point on the scatter plot represents one case from the data set. So you're looking kind of at like, okay, this one person, this is the answer, this is the value that they gave for the x variable, and this is the value that they gave for the y variable. And then you put that point at that intersection, that x and y intersection, right? And it results in a scatter plot where you have, all of these kind of data points, and determining, whether or not there's a correlation, and then developing a regression line. It builds from, that scatter plot. Now, the great thing about scatter plots is that you can actually just usually visually see, your outliers, which, we've previously discussed. How do you figure out if you have individual outliers? But you also can have outliers in terms of, outlier relationships. So data points where the relationship between X and Y deviates in a real significant way from what the other data points suggest. And so, when you're looking at a scatter plot and you see that you have some outliers, it makes you aware of them, so you can then decide how to handle them in your future analyses, whether or not they should be included or potentially excluded so that they don't distort your analysis. So the analysis itself, as indicated, your book discusses two ways. They discuss correlation and they discuss regression. So correlation determines the extent to which two quantitative variables approximate a linear relationship. And they discuss what a linear relationship is. This is where there is this, a change in X is reflected in a change in Y in specific intervals. And although a perfectly linear relationship can exist mathematically, it's actually pretty rare in research findings. And so, the formula for this, y equals bx, in that formula, your b is your slope, which is the number of units that y changes every time that your x changes. And if your slope is positive, you see that your graph, the graph looks, the way that it does, it's that type of diagonal where as your x increases, your y increases. If your slope is negative, then it's the opposite. Your y decreases as your x increases. But as noted, most of your data isn't going to have this perfect linear relationship. So instead, what you're kind of looking for is, going back to our scatter plots, is kind of the general trend. And so correlation analysis, once again, don't worry about mathematically how do you get it, because when you learn how to do this, you're going to learn how to do it using statistical software. And it's, you plug in a command and it gets you what is called a Pearson correlation coefficient, your R. And this is an index that determines the level of correlation between two variables. And your Pearson correlation coefficient, it ranges from -1 to 1. And a value close to 1 or -1 indicates a linear relationship. The closer it is, the more perfect the relationship. If it's close to -1, it's a perfect negative relationship. If it's close to 1, it's a perfect positive linear relationship. And if it's close to 0, it means that these two variables are really just unlikely to be correlated with one another. There isn't much of a correlation existing. So to kind of give you a sense of what this actually would look like in a scatter plot, I give you this graphic, and you can see that Pearson correlation coefficient, that's 0.7, you know, that the points, you know, if you were to then like, you know, plot a line, and we'll talk about that regression line here in a second, but you can kind of see that in general the dots are kind of centralized around that line, and it's demonstrating that positive linear shape. And that's the opposite of like a -0.7 Pearson correlation coefficient, where the diagonal is going in the opposite direction. 0.3 and -0.3, the correlation isn't as strong, and you can see that the dots aren't as centralized. They aren't nearly as close to that line because the correlation isn't as strong. And then of course you can see for 0, you know, that there is no discernible pattern at all between your dots, between your scatter plot dots, your data points. Now, before we talk about that line, before we start talking about regression, just a reminder, why are we discussing these, you know, variable relationships with one another in terms of correlation as opposed to causation? Because I said that these are independent and dependent variables, but I'm talking about them in respect of them being correlated together, not in respect of the IV causing the DV. And that's because, and this is a reminder about material from chapter 4, you know, in order to establish causality in social science, that nomothetic causality, you have to meet 3 criteria. Now, the first the criteria is what we're establishing right now, is correlation. Do these variables seem to go together in some type of expected, you know, expected and consistent way? But then the other 2 aspects in order or characteristics of causality, they go beyond the scope of correlation, and that's time order. You have to make sure that your X occurred before your Y, and this can be hard to establish, particularly when doing cross-sectional data collection and not longitudinal data collection. And then of course you also have to make sure that this relationship isn't being explained by some other variable, right? In which case the relationship that we would be seeing is really spurious. So in order to establish causality, you have to make sure that the relationship is non-spurious, that there are no intervening or extraneous variables, you know, influencing the relationship between your 2 variables of interest. So, you know, oftentimes with correlation, you know, you are unable to show time order and non-spuriousness. So you're just talking about it in terms of correlation as opposed to causation. And so this brings me to kind of the final focus of the chapter, which is bivariate analysis. Because as we've been doing these scatter plots, you can see that they've been inserting like a line on the scatter plot. And regression is the statistical analysis that you use to identify that line. And that line is referred to the regression line, or the best fitting line. So this is you trying to establish, if this is my data, what is the best fitting line that best explains the relationship between these 2 variables. And the regression line is expressed by the formula y equals a plus bx, where your a is the y-intercept, it's the value of y when x is 0. Your b is your slope, right? The change in y for every unit change in x. And then X is the very, you know, it's the individual, you know, data points that you then plot. And you use this equation, and then that gives you, you know, your Y. which would be, you know, where your data point should fall in terms of the y-axis, the vertical axis. And so the goal of regression is just as much to predict future behaviors as it is to explain current behaviors, right? So you can plot it out based on the data you have, but what you're really trying to do is predict future data. Like if I know X and I have my regression line, then that should tell me my Y, right? Even if I don't actually have that data. So that is the goal of regression. And so in the same way that Pearson's correlation coefficient, you know, whether it's positive or negative, and it tells us the direction of the relationship between the variables, the regression line also can be used to discuss the direction of the variables. Is that whether or not you have a positive or a negative slope. Now, just a caveat, way beyond the scope of this class, but just important for you to know, is if a relationship in no way approximates a linear relationship, like maybe it's curvilinear, like a U-shaped curve, you can't even do the Pearson's coefficient, and you can't even generate a regression line. Like it can't be used, because both of those types of analyses are based upon the idea that the relationship between these two variables is at least approximating a linear relationship. So your book just kind of notes that there are other types of analyses that you do for those types of variables that have relationships that are nowhere close to linear. Don't necessarily have to know those other types of analyses, like don't even have to remember their names, but I do want you to know that regression and Pearson's coefficient, those types of statistical analyses are only available and accessible to you if you have a linear relationship. And how do you know you have your linear relationship? Well, you can, like, you know, roughly eyeball your scatter plot. So this is once again why putting your data into the software program and generating that scatter plot even before you run any specific analyses is just useful and helpful. And so that is it for chapter 10. Like I said, don't get bogged down overly much into the math. It's more important that you kind of understand what the logic behind these analyses are and what these numbers are telling you. Less important in my class that you know how to get these numbers for yourself.